For this system of equations, we call it a system because we have more than one equation. It is a system of differential equations, since each equation involves derivative. You see, derivative of x, derivative of y. So have two equations. I want to remind you the meaning of x and y. Remember in the first equation, x as a function of t represents a population of the predator at time t. The function y of t is the population of prey at time t. So they're both functions of time. As long as we remember that we can simplify our writing. For example, we can remove the parentheses t, so just simply use the name x as name of the function, y name of the other function. So we can just take out the parentheses t, but always keep in mind they are functions of t. So we simplify our writing like this. So here, A, B, C, D are coefficients. And they are positive coefficients. We know that let's solve this system of two equations for the constant solutions, because the constant solutions are simple solutions. And let's discover if there exists at least one constant solution for the system. So that is, if x and y are both constant functions, then derivative of x will be 0. Thus, the first equation becomes if y is a constant function, and then derivative of y will be 0. cy minus d xy. So then the differential equation becomes algebraic equations. That means let's just solve this. That means no more derivatives in each equation. So we are looking for x and y. Each is a constant function. So from here, we can continue to work on each equation. But x in the first equation can be factored. So let's put 0 on the right-hand side just to make it a little bit easier to work with. X is a common factor, so we factor out x. So that's first equation. Second equation, we also put 0 on the right-hand side, and we factor out y, which is a common factor, and c minus d x. And this equation does not involve the derivative of x or y. So we can use the product rule, actually 0 factor property. So if the product of these two quantities is 0, at least one of them should be 0, right? So that means x is 0 or the other factor is 0. So then we can find either x is 0 or the second factor is 0. That means y is a over b. Then the second equation, if the product is 0, then one of the two factors has to be 0. That means either y is 0 or c minus dx is 0. That means x is c over d. So therefore, we have found one solution, which is x equals 0, y equals 0. That's a solution for the system. Or another solution, that is x is c over d, y is a over b. So let's write the two solutions. So that means I'm going to, so this, yeah, so let's put the two solutions. So when x is 0, y is 0, let's just simply put 0, 0. Or when x is c over d, y is a over b, we can write this solution pair like this, because both x, y are constants. So the first value in this pair is x value. Second value in this pair is y value, just like 0, 0. So x, y. So we found two solutions, two constant solutions. Each constant solution is called equilibrium solution. So these are the terminology for the constant solutions, which we call equilibrium solutions. So those are the constant solutions, right? So that's one equilibrium solution. And those are this is the second equilibrium solutions. But when we put it in the ordered pair, so the x, y as both constants, then we have a point. So this 0, 0 is called equilibrium point, or the second point is also an equilibrium point. So we can show the either solution or the point. Let's look at a picture of this. So if I draw the solution curve, so x, actually x, we can put t here because x is a function of t, so we will put x vertically, and this is t. If we want to show the solution curve, then if x is 0, that means this is constant solution, right? Y is another constant curve because we have found y always equal to 0, so we can draw the y. So here is x equals 0, y equals 0. They're both constant functions. But if you want to show x, y as a point and try to make t implicit, so we can draw the xy plane we can draw XY plane, which is, okay, so let's say X horizontally and Y vertically. So here, where is T? T is not explicitly shown here, but X, Y, they are always 0, right? X value is always 0, Y value is always 0. So on the XY plane, the constant solution will be a point. So that is 0, 0 as a point. So similarly, we can look at another constant solution we found. Remember the X is C over D. Y is A over B. So if we draw the X as a function of T, so X and T as X as a function of T, so this is a constant, right? So C over D, just C as a coefficient over D, another coefficient, that's a constant. So C over D is just a value. And we can, let's suppose this is C over D, which is positive, and then it is always that constant. So we can draw this constant solution. And Y, same thing. So if we draw the Y versus T, Y as a function of T, but since this is another constant, A over B is a constant, so we can draw A over B. So suppose this is A over B, A over B. And then that's a constant solution. However, if we draw X and Y plane, so we can show XY without explicitly showing T. So X as horizontal axis, Y as a vertical axis. Then the X value, which is C over D, Y value, which is A over B, and XY are both constants. So this pair must be a point, right? So it is X C over D, Y A over B. So this is the point. So I'm going to make it a little star. That's the point. That's the point. So this point, we have a name, we call it equilibrium point. Yeah, just like 0, 0. That's another equilibrium point. So we have found 2 equilibrium points for this autonomous system of equations. Yeah, equilibrium points. Okay, so now just see those 1 point and second point. So we have 2 equilibrium points. But we know actually the predator-prey model has other solutions. So we have actually periodic solutions according to Volterra's first law and second law. So Volterra, yes, he discovered additional results. So we're going to look at some interesting results. Volterra's laws. So I want to, the first law, the law of the periodic cycles. Okay, the law of the periodic cycle. So this is the Volterra's first law. Yeah, this is Volterra's first law. So it says the fluctuation of the population of the predator and its prey are periodic. That means in addition to constant solutions, there are periodic curves. Yeah, other solutions as well. And the period can depend on the coefficients of the equation or the initial data. And the period increases with the amplitude of the corresponding cycles. But I don't want to go in detail, so it's just for you to be aware that in addition to simple constant solutions, which we call equilibrium solutions, or equilibrium points, we also have periodic solutions. The second, Volterra's law. Okay, let's use the theorem. It is actually the law of averages. The law of averages. It is Volterra's second law. So this law basically says if it's a periodic solution of the predator-prey system, and the average predator population and average prey population will be this value. So let's use X bar to represent average of the predator. It will be C over D. And the Y bar to represent the average prey population will be A over B. So this is very interesting. That means what we found, this is a constant solution, right? C over D is in fact a constant solution. A over B is also a constant solution for prey. So the C over D over B is the equilibrium point if we put them together as a point in the XY plane. So that for some periodic solutions, the overall average of that solution over a period is equal to this constant. And same is true for the Y. If Y is a periodic solution, the overall average of Y over a period is A over B, is equal to that constant. So that is a very interesting result. So let's look at one example. I think we know one example. Let's just use this particular system. And from this example, we have already worked on this problem. And you know ABCD. Here in this problem, what is A? Could you see? Looking at the formula, right? The A is actually 1. You see, A is 1 here. What is B? B is 1/10. What is C? C is also 1 here. D is 1/5. Yeah, A, B, C, D. And then let's check on the formula says C over D, right? X. So if C is 1 over D is 1/5. 1 over 1/5, which is 5. Yeah, that's what we got. So Y, A over B. A is 1. Here, 1. A over B. B is 1/10. So A over B is 10. So that's 10. So it's just to show you that a general formula has been derived for this specific case. We just derived a formula for whatever ABCD, but this is a specific case. So we can find the constant solution using that way, right? We just look for X and Y, which are constant. So we can find constant solutions for this system. This system has a name. It's this type of models. We call it autonomous, because if you look at the system, so let's say this. Do we see Y? No, do we see T? T is not explicitly so showing on the right hand side. So this system, of course, X and Y are both depending on T, but there's not a T variable, right? So the right hand side is only an expression of X and Y. So this, if the right hand side of each equation in the system depends on the unknown functions only. Yeah, if it does not depend on T explicitly, then this system is called autonomous. So for autonomous system, we can find, we can try to locate constant solutions or equilibrium solutions or equilibrium points. So now a question for you to think about. The question is, think of some harvesting. So if I have a system, the system we know already, and if we do harvesting, so this is edge, some addition, a constant coefficient, because you harvest both X and Y, so it will impact the predator population and prey population, and assuming the H is the same for both species, right? But if they're different, we can put a H1, H2. Yeah, so that is probably more reasonable. Yeah. So, but the y, we know the original equation has the term y and minus xy over 5. But the only difference for this new system is we introduced the harvesting. So harvesting, this is a new model because we have a new term. Yeah, we have a term because of the harvesting of the prey, harvesting of the predator populations. So this harvesting will affect both populations of prey and predator. So the question for you is, what will be, so the first question, can you find constant solutions of this system with harvesting, right? So the question 1 is for you to find constant solutions or equilibrium solutions of the system, if there are any. So please find them. Yeah, so how will with harvesting, right? How will this affect the predator and prey populations? That's a second question. With harvesting, so actually I would say, how will harvesting affect or will harvesting affect predator and the prey populations? We can use X bar or average predator or prey populations. Okay, so these are the questions for you to think about. But for the new system, the method is the same. So let's find the constant solutions, and then the constant solution, remember, can explain the average of the predator population and average of the prey population. Then we can see how the harvesting can impact the average of each species. Okay, that's all for now.